Hey everybody, so in lieu of an in-person review session, I thought I'd record this video for you, so welcome to your review session. The test is exactly the same as every other that we've taken so far. It is 90 minutes long. There are 15 multiple choice questions. Those will be worth 2 points each. Rather than a lab-based question, since most of our labs have been mainly qualitative this time, I've got a diagram for you to complete for 10 points. Then there are 5 free response questions, again for 10 points each. Just as with every other test, bring one sheet of paper front and back, bring a calculator, and do try to let me know ahead of time if I need to have a calculator out with your name on it. First thing you need to know is about elementary charge. Basically, the proton, the electron, they've got the exact same charge even though they have different masses, except one is positive and one is negative. Sometimes you'll see this as just lil e in textbooks. It's called the elementary charge. So if I gain one extra electron, I have a net charge of negative 1e, and so on and so forth. Or if you want to put it in terms of base units, that would be negative 1.6 times 10 to the negative 19 coulombs. I will give you this constant on the test. So we've got protons and electrons with the same charge but different masses. Meanwhile, neutrons, they have no charge. Few things you must know about charge. It's that it's quantized, meaning I'm not going to get half an electron charge or half a proton charge or anything like that. It's all going to be integer multiples of that elementary charge, of that 1.6 times 10 to the negative 19 coulombs. So I can have a small fraction of a coulomb, that's fine, but I can't have a fraction of the elementary charge. And all charges are conserved, so you're not just going to get negative out of nowhere or anything like that. Then we leapt into Coulomb's law with the equation F equals K Q1 Q2 over R squared, where K, which is a value I will also give you on the test, is 9 times 10 to the 9th Newton meters squared per Coulomb squared. This means any two objects that have some sort of a charge will experience the exact same force toward each other. Object 1 will experience kq1 q2 over r squared. Object 2 will experience kq1 q2 over r squared. If you've got multiple charges and you want to find the net force on, let's say, one of them, break it down one at a time. Find the force due to object 1, due to 2, due to 3, and then use vector addition to find the net overall force. The triboelectric series, you're just going to need to know basically how it works. The farther up the scale you are, the more positive you're going to be, or the more likely you are to give up electrons and become positive. The farther down the scale your material is, the more likely it is to take electrons and become negatively charged. So if I rub, let's say, polyethylene and wood together, odds are the wood will become positively charged, polyethylene will become negatively charged. Alternatively, if I rub wood and wool together, then odds are the wood will become negatively charged, the wool will become positively charged. Grounding is just this idea that I can connect something. Sometimes it actually is physically the ground, sometimes it's just some other reserve of electrons. But it's this idea that you're connecting it to essentially an infinite reserve where electrons can come and go as they please. They can stack up if something's positively charged, they can leave if something's negatively charged, or if you trick it into thinking it's positively or negatively charged, you can use grounding to actually charge an object, and that's called induction, which we'll get to in a second. Make sure you understand the difference between conductors and insulators. Both can be charged, and that's a lot of times a misconception, that just because insulators do not allow electrons to move freely, they think you can never hold a net charge, but you can. You just stack up the electrons all in that one spot. Conductors get charged via conduction and induction. Insulators, you just rub them against something else. And that's really the main difference. It's just if electrons freely flow. Within polarization, insulators can become atomically polarized. Their little atoms can realign themselves, but the electrons are not free to move throughout the object itself. Whereas conductors, that is the case. Electrons can totally travel all around the conductor if they want to. So polarization, just like if you ever hear Washington, D.C. is so polarized, it means the different ideologies are spreading farther and farther apart. Just like here, the charges, the positives and negatives, are spreading farther and farther apart. But beware, the negatives are the only ones that are actually moving. Protons are locked in place. Be sure you understand the difference between conduction and induction. Conduction, contact. Induction is, I call it charging by trickery. With conduction, you'll probably end up with two objects of the same charge, and with induction, you'll probably end up with objects of opposite charge. So just be aware of that. Here are just a couple of pictures of it. Oh, by the way, this entire PowerPoint is also on Canvas. If you log in and go down to Modules, Old Test Solutions, and Review, it's Test 4 Review. So you'll find the full PowerPoint there, if you want to look at that. You can also just look directly at the module PowerPoint itself. So if you find any parts of conduction or induction confusing, I'll let you hop onto the PowerPoint, or you can pause the video as I go through these slides of these images and take a look at what exactly is going on. And then we moved on to electric fields. Electric fields are a little bit more complicated because, well, forces are kind of easy. You've got objects physically there, and the objects are physically feeling that force. Electric fields are a little bit different. You don't necessarily have to have something there. There could be. I don't want you to think that if an object is present, there can't be an electric field in that space, because there totally is. But it is the depiction of force that a positive test charge would feel if brought near a charged object. So it always points toward negative charges. It always points away from positive. And you can find the magnitude of that electric field as just kq over r squared, where q is the charge of the object creating the field, E is the electric field in newtons per coulomb, so it's just how many newtons of force per coulomb of charge am I getting. R is the distance away from the charge you'd like to measure the field, and K is good old Coulomb's constant. It's a lot like the force equation, except only one Q to worry about. Do familiarize yourself with the most common interesting electric field shapes. So a dipole, one positive charge, one negative charge. All the field lines start at the positive, and they branch away, arc around, and direct themselves toward the negative. Be aware of the two negative and two positive types of styles as well. Not only that, make sure you know what the electric field looks like within lines of charge. So if I've got a capacitor, it's going to get a plate. One plate will be positive Q, one plate will be negative Q, and the field line is actually in the middle, a perfectly straight line away from the positive and toward the negative. Once you get to the outside edge of these lines of charge, then it starts to look just like a dipole with the curving. But in the middle of it, it's a straight line, which is kind of helpful because you can achieve different voltages at different values that way pretty easily. So just be aware of those electric field shapes. A few rules about sketching electric field lines. The more lines that are coming out of an object, the stronger the charge it is. Field lines can never cross because there can be no location where there are two net forces at once. And the electric field are vectors, so be sure to treat them like you treat any other vector. Now, an example of something that is not a vector is voltage. Voltage, also known as electric potential and potential difference, and sometimes just potential, is a scalar. And all that really determines voltage is some sort of charged object and some distance away from it in space. Basically, it's just the amount of energy in joules per coulomb, so the units would be joules per coulomb, or a joule per coulomb is just the same thing as a volt. But the equation is just V equals kq over r. A lot of these equations are really similar, so be sure that you take the time to just separate out in your mind what a force is, what a field is, and what voltage is, what electric potential is. A lot of times you'll see equipotential lines. These are regions of equal voltage. So it's kind of like a topographic map. The closer together the lines are, the greater the change in voltage. Oh, by the way, electric field in newtons per coulomb is the same thing as volts per meter. So if I know the field strength in a region of space, then that'll tell me for every meter that I travel with that same field strength, it tells me how much change in voltage there's going to be. Cool. A few notes on vectors versus scalars. With vectors, definitely ignore values of Q at first. So vectors are going to include forces and fields. If you're solving for something that starts with an F in this unit, odds are it is a vector. No, that doesn't work. Anyway, so ignore negatives of Q at first and just solve for the magnitude. Magnitude, again, is an absolute value. Then determine the direction yourself. The reason that negatives are so dangerous for vectors, at least in this unit, negative charges, is if I've got like a negative charge over here, and I want to find the electric field at a point to the left of it, then that electric field is going to point to the right. But if I plug in a negative Q, I'm going to get a negative value, and it'll be tempting to point it to the left, and everything's just wrong. So ignore the negative, figure out the direction for yourself based on that negative later. Versus energy and voltage. Energy and voltage are both scalars. So it's just a value. That means the negative has a direct impact on that value. So do not ignore it because there is no direction. The nice thing about energy and voltage is that you don't have to worry about breaking things into x and y components. For forces and fields, you might have to. And then I mentioned on a video, briefly at least, about capacitance. Again, these are where you have two parallel plates. One gets charged plus Q, one gets charged minus Q, and the electric field is perfectly straight in between them. And this idea of capacitance is this. Based on these charges, I'm going to get a change in voltage between the two plates. Capacitance is just the ratio of charge per voltage. So I get coulombs per volt as my unit of capacitance, and that translates to farads. The main purpose of capacitance is to store energy, electrical energy, and release it very quickly, as quickly as you need it. A lot of other electrical components can't quite do that. So it just briefly holds energy and quickly releases it. Speaking of that energy, you can solve for that energy in joules. The energy stored up in a capacitor is just 1/2 times Q, that's the charge in coulombs, times the change in voltage in volts. I could also rewrite that, since I know Q equals C delta V for a capacitor. I could rewrite this energy equation as 1/2 instead of Q. I'm going to put C delta V in there times delta V, or U equals 1/2 C delta V squared. So I can find the energy directly just by knowing the capacitance and change in voltage between the plates, if I need to. All right, so a quick little recap of the equations, just because a lot of them are so similar. And there are only a few equations, actually, that you need to know. Over in vector land, you're going to have to deal with forces and fields. So let me quickly jot down the equation of force for you. Whoops. F equals K Q1 Q2 over R squared. Then you may also encounter electric fields. And that equation for those fields is KQ over R squared. Then over in scalar land, we've got energy and we've got voltage. The energy equation I didn't mention earlier, I'm probably not really going to hold you much responsible for, but in any case, here it is. The energy between any two objects with charge is K times Q1 times Q2 over R, not R squared. And that's really tricky, because that's very similar to the equation for force. Similarly, The equation for voltage is really similar to the equation for electric field, but the R isn't squared, and it's a scalar, not a vector. And that's V equals K times Q over R. So be very, very certain that you carefully separate this out, read each question, and understand exactly what's being asked. If you do that, I think you all should be fine. All right, take care.